Hello everybody and welcome back again. This example 6, is going to be a little bit of a departure from the problems that we have been working on. We've been dealing with problems dealing with relative motion, and that is largely what this chapter is going to be about, but it's also going to be a little bit about kinematics, 2D kinematics, two-dimensional kinematics. And now this is only in one dimension, that is acceleration in just along a straight line. But this is going to sort of set the table for the 2D kinematics vector problems that we're going to be doing a little bit later on, okay? As well as problems that deal with relative motion, kind of like we have been doing, all right? So my goal here is to do part A and part B, and maybe we'll save part C for a different video segment, okay? So we've got a car traveling at 25 meters per second. Right away, what can we call that? Well, we can call that an initial velocity, right? It's currently, or it's initially traveling at that speed. So initial velocity equals 25 meters per second in a direction 25 degrees east of south. All right. Well, we don't like this because east of south, you're basing your angle off of the vertical axis. We don't want that. Think of it like this. There's our north-south, and there's our east. Okay, this is our, excuse me, there's our south right there. And so 25 degrees east of south will look like this. All right, that's our 25 degrees in there. There's south, and then there's east of it. Well, we don't like that. We want our axis, or we want our angles based off of horizontal axes, not vertical, because otherwise it flips around all of our trig functions that we're used to using. So if that angle in there, if that is 25 degrees, that's 25 degrees, then what does the complementary angle, let's make that green, what does this have to be? Because this is what we really want, because that's based off the horizontal. This would be south of east. East and then south of it. So if this whole thing, east and south, make a 90-degree angle, and that's 25, then we can conclude that that angle south of east is going to be 65 degrees. 65 degrees in there, all right? So let's go ahead and change that. Instead of 25 degrees east or south, we're going to say 65 degrees south of east, and then we have it based off of our horizontal, and we don't need to worry about our trig functions being all messed up, okay? All right, so the driver hits the brakes. This car is driving in a straight line, and the driver hits the brakes. It applies a deceleration, all right? And so it comes to a stop. Well, wait a minute, what can we call that stop? That stop is a final velocity, right? So the final velocity is 0 meters per second. V final equals 0 meters per second. Does it happen immediately? No, it happens 0.34 seconds later. So that's going to be, let's do that in purple. That's our time right there. 0.34 seconds, that's our time. 0.34 seconds. All right, so we want to find the car's change in velocity, delta V, in two different notations. We want to find it in unit vector notation and in magnitude direction notation, okay? In fact, I'm going to do magnitude direction notation probably first, all right, and then we'll solve for it in unit vector notation. We want to find the car's change in velocity. So what I'm going to do right here is shrink all this down so we have some more room to work with, like that, okay, and I think that'll do, and I'll lock that in place. Okay, so a change in velocity. What is that going to be? Well, first of all, let's draw our vector. Our vector is going to be look kind of like this. All right, that is 25. You might say our initial velocity. Our initial velocity equals 25 meters per second. And I just kind of wrote in there where the angle would be. You know, I'll draw this below. Or a little bit lower down. Here's our angle based off the horizontal. And that we said that was 65 degrees, right? So theta equals 65 degrees. And so this vector represents our initial velocity of 25 meters per second at that 65 degrees south of east angle. Okay? Okay, so that's our initial velocity. What's our final velocity? Well, final velocity equals 0, right? 0 meters per second. That's not hard. All right, so our change in velocity, or delta V, is going to be V final minus V initial, because delta always means change, and change always means final minus initial. Okay? So, what should we do? Well, we should, first of all, I think what we should do is take our vector and break it into x and y components. All right? Now, I'm going to draw our vector again one more time right here, a little bit larger. All right, so here's our V initial. Okay, V initial equals 25 degrees at 65 degrees south of east. Okay, and it has x and y components. So we're going to need to know them anyway because we're going to eventually need to write it in unit vector notation. And unit vector notation deals only in x and y components. So, what is our x component? Well, it's going to look kind of like that. V initial x. And our V final x, I always do the y. Oh, sorry, V final, let me back up. V initial y direction. I'm getting ahead of myself here. It's going to look like that. V initial in the y direction. Well, how do we get the x? Well, x is always magnitude times the cosine of theta, right? So that's going to be 25 times the cosine of 65, and what I get is 10.56. Let's go 10.6, all right? 10.6 meters per second. 0.6 meters per second. And our y value is going to be 25 sine of theta, right? 25 sine 65, that is 22.7, I round to. 22.7 meters per second in the y direction. 22.7 meters per second. Oh, but wait, it is negative y, right? So we've got to put a negative sign in front of it. Don't forget that. All right. So let's find our change in velocity in, I'm going to do unit vector notation first because we took all this time breaking it into x and y components, all right? So what is that delta y right there? Delta y is y, oh sorry, not delta y, delta velocity, delta v. Delta v, change in velocity, is going to be v final minus v initial, okay? Well, we can subtract unit vectors, right? If we subtract unit vectors, if we have the x and y components of this vector right here, we can write it in unit vector notation. So v final is going to be 10.6 meters per second x hat, right? 10.6 meters per second x hat, and that f in the final doesn't look very f-like. Neither does that, but I'll just rewrite it. V final. Final, okay. And what component in the y direction? Well, it's going to be negative. It's going to be negative 22.7. Negative 22.7 meters per second y hat. All right. Oh, wait a minute. Is that our initial? I'm sorry. I took all the time rewriting the f for final. It's not even final, right? That's our initial velocity. V initial. V initial is that. And that's what we took all this time illustrating up here. V initial x, V initial y. That's our V initial in unit vector notation. What is our final velocity in unit vector notation? Well, it's not going to be hard. V final equals 0 meters per second x and 0 meters per second y, because it's at stop, it's at a rest, all right? So it really has no direction because it has no magnitude, all right? So that means delta V is going to be 0 minus that 10.6. I should do all this in green, I suppose. I guess I should have done the other ones in green too. excuse me for a second. There we go. 0 minus 10.6 meters per second x hat. Okay, and it's going to be 0 minus, what is it? Negative 22.7 meters per second y hat. 0 minus negative 22.7 meters per second. That's in the y hat direction. All right, and that simplifies to, and now I will just use all red. Our delta V in unit vector notation is going to be negative 10.6 meters per second x hat. That's an x hat right there. And 22.7 meters per second in the y hat direction, like that. That's our answer for our change in velocity in unit vector notation. All right, that's part A1. Actually, we're probably only going to get through part A in this this video segment right here, but that's fine. Okay, so part A. So we've got this right here, unit vector notation. What we want now is a magnitude direction notation. All right, so the change in velocity, the magnitude of the delta V is going to be what? Well, if we have the x and y components, the change in y component, change in y is going to be the square root of the x squared plus the y squared, all right? 10.6 squared plus 22.7 squared. I didn't put the negative 10.6 in there because the negative is going to go away anyway. But this is going to give us our magnitude of this vector, all right? This change in velocity vector. 10.6 squared plus 22.7 squared to the 1/2 power, 25 meters per second. All right, 25 meters per second, and that should sound familiar to you. All right, that was the original velocity, and if it comes to rest, then we can say our change in velocity is 25 meters per second. All right, at what angle? Well, it's going to be inverse tangent of what? Of our y over our x. That's 22.7 over 10.6. Again, I left the negatives out because we can just use the absolute value. What's that angle going to be? Inverse tangent. 22.7 divided by 10.6. Did I get that right? Yes. 65 degrees. That should sound familiar too. 65 degrees. Now the only last question we need to answer here, and this is what's going to be different. So our original velocity was 25 meters per second at 65 degrees south of east. But our change in velocity is going to be in the opposite direction, because if you have this initial velocity right here coming to rest, then some change in velocity is going to have to act against it to bring it to rest or to bring it to zero. So what is this? What is the quadrant? Well, we've got a, let's see, we've got a positive y and a negative x. So it's going to look like that, right? So what quadrant is that? That's north of west. North of west. So that's our direction. Kind of weird box right there. And that's our magnitude. So we could say really our delta V, I'll put it all in one right here, is going to be 25, our change in velocity, we should say, is a 25 meters per second at 65 degrees north of west. Or that is acting against the original direction of motion, because it's that change in velocity that brings the original velocity to zero, to rest. Okay? So in the next segment, we're going to continue with this and take this change in velocity and turn it into an acceleration, which is going to be actually a lot easier than you think. We've done pretty much all the hard part. I might make a decision on C whether to or not to do that at all, but we're definitely going to do part B in the next segment. All right? So thanks for following along, and in the meantime, make sure you ask me if you have any questions, and I'll see you on the next one.